Hello, everyone. It's Wednesday. It's almost the middle of the week. So, what better time to to reach the middle of Advent of Code? Right. So, we're doing Advent of Code. This is a programming competition. It runs between 1st and 25th of December. There's a new challenge every day. Each challenge has 2 parts, but we only see part 2 after doing part 1. We've been doing these on the day every day. And today we're going to be doing day 13. But before that, a bit more background. Advent of Code is a competition in the sense that there's a leaderboard and some people compete to be the first to solve the problems each day. Most people, however, use this as an opportunity to learn something new. This works quite well for Advent of Code because the difficulty ramps up every day. So the first few days were very easy, and then it's been getting more and more challenging. Yesterday's problem was quite interesting. Well, I'd even go so far as to say lovely. There was an obvious solution that was too slow, then there was a slightly better and more intricate solution that involved recursion, but that also was too slow, and then that needed a bit of memorization and caching in order to get it up to the speed necessary to actually solve the whole thing. This was nice. It was the first time, it was the first time this year that the problem was so intricate. So the challenge for me, or the challenge for us this year, is to do this in Elixir Livebook. Livebook is this nice little web app that lets you basically execute Elixir code in the browser. I mean, it's actually being executed on a server and the results are sent to your browser, but it looks like it's done in your browser. Livebook lets you interleave text and code, and whenever you have a bit of Elixir code, it also computes the result of that code underneath. So for example, here's the fast solution to yesterday's problem, and bam, here's the result. Elixir Livebook also has some fancier features, like for example, it can generate input elements, like here's a text area, and this is how we've been getting our examples and full problem inputs into the code. This feels nicer than just hard coding strings into the source file. But then it has even fancier output capabilities. For instance, yesterday, we wanted to see what the actual execution graph for our recursion looked like. And here we are. We just generated a mermaid chart that shows exactly how our code is being executed. And whilst this didn't help much in debugging, it was nice to draw it afterward and see what it all looks like. And another superpower I hadn't realized that Livebook has until yesterday was that this whole thing where you have multiple blocks of code and then multiple outputs is extremely useful. Yesterday, we first solved part 1 in a slow but obviously correct way. And then we solved it again, but fast. Being able to see both the output of the slow code and the output of the fast code side by side was extremely helpful in debugging. Doing this with actual programs that you execute on the command line would have been less clear. It would have required more juggling it would have required juggling more displays, and it would have required keeping more things into memory, as in human memory. And yeah, this was helpful. So now, without further ado, let's see what's in store for us today. Hello y'all, Future Alex here. Today's problem was easy and brute forceable, but frustrating due to a tricky problem specification. We solved part 1 easily enough, and part 2 was not much harder. However, there were corner cases, so we didn't get the right answer on the first try. I failed to find all the corner cases, so we ultimately had to check the subreddit for hints. The challenge for you, then, is to see if you can spot the corner case that I missed. So, Day 13, Point of Incidence. With your help, the Hot Springs team locates an appropriate spring which launches you neatly and precisely up to the edge of Lava Island. Now, as a reminder, we're traveling across the Kingdom of the Elves in order to fix the snow machine. We are nowhere near close to fixing the snow machine. Yesterday, we fixed the hot springs. As in not hot mineral springs that are filled with therapeutic water, but springs that you have to heat up in order to launch you into the air. There's just one problem. You don't see any lava. Alright, and Lava Island... We need to fix the lava on Lava Island so that the forges can have lava to melt iron to produce the machine parts necessary to fix the sand machine, whose sand we need in order to filter the water for the snow machine. We're on a bit of a scavenger hunt here, and it's getting insane a bit. Anyway, let's solve the problem. You do see a lot of ash and igneous rock. There are even what look like gray mountains scattered around. After a while, you make your way to a nearby cluster of mountains, only to discover that the valley between them is completely full of large mirrors. Most of the mirrors seem to be aligned in a consistent way. Perhaps you should head in that direction? As you move through the valley of mirrors, you find that several of them have fallen from the large metal frames, keeping them in place. The mirrors are extremely flat and shiny, and some of the fallen mirrors have lodged into the ash at strange angles. Several of the mirrors have fallen, and they are lodged into the ash at strange angles. Because the terrain is all one color, and it's hard to tell where it's safe to walk and where you're about to run into a mirror. Because the terrain is all one color, it's hard to tell where it's safe to walk and where you're about to run into a mirror. Oh, so we're basically in a funhouse mirror. Yeah, we're in the mirror house at a fair, except it's a desert. You note that the patterns of ash, dot, and rocks hash that you see as you walk your puzzle input. Perhaps by carefully analyzing these patterns, you can figure out where the mirrors are. For example, to find the reflection in each pattern, you need to find a perfect reflection across either a horizontal line between two rows or across a vertical line between two columns. Why is there a space here? You note out the patterns that you see. In the first pattern, the reflection is across a vertical line between two columns. Arrows on each of the two columns point at the line between the columns. So this is the first... Oh, so there are multiple patterns, and they're going to be separated by an empty line. And the patterns, they say it has a reflection here. Does it? Yes, although it's not a complete reflection. In this pattern, the line of reflection is the vertical line between columns 5 and 6. Because the vertical line is not perfectly in the middle of the pattern, part of the pattern, column 1, has nowhere to reflect onto and can be ignored. Every other column has a reflected column within the pattern. Every other column has a reflected column within the pattern and must match exactly. Column 2 matches column 9, column 3 matches 8, 4, 7, 5, and 6. The second pattern reflects across a horizontal line. Yes, and this does look like a reflection, although again, it is not a complete reflection. This pattern reflects across the horizontal line between rows 4 and 5. Row 1 would reflect with a hypothetical row 8, but since that's not in the pattern, row 1 doesn't need to match anything. The remaining rows match. Row 2 matches row 7, row 3 matches row 6, row 4 matches row 5. To summarize your pattern notes, add up the number of columns to the left of each vertical line of reflection. To do that, also add 100 multiplied by the number of rows above each horizontal line of reflection. In the above example, the first pattern's vertical line has 5 columns to its left, and the second pattern's horizontal line has 4 rows above it, a total of 405. So 4 times 100 plus 5. Find the line of reflection in each of the patterns in your notes. What number do you get after summarizing your notes? Okay, so can obviously brute force this by just... Whether we can brute force this or not depends a lot on what our full input looks like. So let's look at our full input. Okay, so there are a lot of patterns, but none of them seem particularly long. In particular, none of them seem like they're longer than 32 bits. So my immediate thought on looking at this is that there are only two possible characters, so we can encode this as bits, as numbers. And this matters because we essentially have to compare lines here. And comparing lines one character at a time is slow. But if we can first convert the numbers into integers, say into int32s, and then compare those, that's fast, because computers are very fast at comparing int32s. And unlike yesterday, we don't have any wildcards or anything of the sort, so we truly have just the bits here. So in order to do this, we first need to check what the maximum size of each pattern is. We need to create integers out of every line and out of every column. So we care basically about both dimensions of each pattern. If they're less than 64, we can go ahead with this plan of converting lines and columns to integers and then just manually comparing manually trying every reflection point. Right, so once we have the integers, let's take this example. Once we have an integer for each of the numbers, then we're just going to go once through all of the lines, or rather through all of the spaces between the lines, and see if this is actually a reflection, going up and down. And this is going to be, on the one hand, linear because it goes through all of the lines once, and then it will go through all of the lines again, up and down. So this will be a quadratic algorithm. It will be a quadratic algorithm that at every step compares two integers. If we didn't do the integer thing, it would be a cubic algorithm, because we'd also have to iterate through the columns. So we do once the quadratic algorithm for all the lines, and then we're going to do it again once for all the columns. Yeah, this feels doable. But again, first step, we're going to parse the input, and then we're going to output the maximum dimensions of every pattern. Yes, we're going to output the maximum dimensions of every pattern. So we're doing this in Livebook. So first off, we start a new notebook. We will call this notebook AoC 2023 Day 12. Ah, no, today is Day 13. And I should update the stream info. Yes, we are doing Day 13, definitely. So this is Day 13. Then we save it to avoid any unfortunate accidents later. As always, we will need Kino as an input. Kino is the Livebook library that handles all of the user interaction. We're going to use it both for inputs, like say here where we're going to read our example and full input, and it's also used for several output types like the HTML or the mermaid graph or the mermaid chart output. The first section is going to be called inputs. And we start by having example is a Kino input text area. We're going to have a second text area for the full input. Now let's copy the stuff in so that we don't have to keep switching tabs. That was the example, and here is the full input. Next up, we're going to have a section called helpers because we usually end up needing this. But then we're not going to put anything in it. We're instead going to start with part 1. So first things first, let's try to parse our input. So kino input read example. This gives us the contents of this text area as a single string. So then we split on double new lines because the double new lines separate the patterns. And now we have 2 patterns. And then for each pattern, we're going to have to do something. So we enum map over the list of patterns. And this is just strs for now. Actually, let's call it lines. Okay. First thing we do with our lines is we split them on new line. Because each pattern is composed of multiple lines. We see that we have an empty string at the end of the last pattern. This is because we have an empty new line at the end of our input. So we do trim true. And now we've gotten rid of that empty string. Next up, well, all right, so first off, I want to do a bit of experimentation. I want to see how big these patterns are. We can do this here because advent of code is unusual as far as programming competitions go, because it actually tells you all of your input at the start. Like in most programming competitions, you get some examples, but then you submit your program and then it's run on some secret inputs that you don't know about. But advent of code is different. It gives us the input. So we just need to write a program that works on this and on this. We don't need to support any bigger inputs. There's a bit of fuzziness here because we don't know what part 2 is going to ask of us. So there's a fair chance that part 2 is just going to say, oh, this was actually a single pattern all along, and the new lines should be ignored. So then we'll have a much bigger pattern. But we'll get to that when we get to that. Let's focus on part 1 for now. And right now, I want to know the size of all of these patterns. So I want to know 2 things. For each of these lines, I want to know the number of elements and then the maximum length of each line. So we're going to say lines is length of lines, and calls is just columns. Columns is we take the lines, then we enum map through them and call string.length on each element. And then we call enum.max on this. So here I'm using the shorthand, the Elixir shorthand for just calling a function that is already defined by its name. So here we're saying we're calling the string length function that has arity 1. It only takes 1 argument. And we call this over every one of our lines, and then we just take the maximum value. Okay, so here we see that the patterns in the example all have 9 columns and 7 lines. I wonder what this looks like for the full. Well, there's a lot of numbers here, so let's compute some more maxes. Let's compute some more things. Yes. So first off, let's just manipulate this a bit better. Instead of returning a map that has nicely named lines and columns, we're just going to return a tuple. Next up, we're going to unzip this list of tuples. Unzip is the operation that takes a list of pairs and then returns a pair of lists. So the first tuple was 15, 11, and the second one was 7, 11, and 15 and 9, and so on. So now we have 2 lists. And since we have 2 lists, we can call enum max on them. So this was lines and this was columns. And then we return, and this is actually a tuple. Now we can return enum max of each of these. So our maximum is 17 by 17. Maybe not even at the same time. But this casually fits into an int 64, so we can go ahead with our plan of turning our inputs into integers and then comparing those. Okay, so we delete this, and now we should just get the lines. Now, for each pattern, actually, let's switch back to the example since that's a bit shorter and easier to reason about. So now we have our first pattern. First, we need to compute two lists of numbers. The first list of numbers is these things turned into integers. So actually, this is going to return a map. I've found that it's very helpful to keep all of your data and intermediate state as you work through this. And then we're going to have lines bin. Lines bin is going to be our lines converted into numbers. Lines bin is, we take the lines and then we enum map through them, because we have to do something different for each line. And then for each line, we're going to do a string replace first. Line. String replace. And we're going to replace hashes with ones and dots with zeros. It's not called string replace. Oh, this has to be the string 1 and the string 0. Okay, so now we have these converted into something that looks a lot like binary digits. And I think here we can do string to integer, and we can specify the base. So if I do string to integer 2, this should work. And does it work? Our first example had... how do we even check this? Okay, well, we see that there's indeed a point. Is there a... The second one had a point of reflection somewhere, didn't it? Or was it the first one? In the first pattern. The second pattern reflects across the horizontal line instead. So the second pattern should have some sort... Yes, here we go. The second pattern does indeed reflect over the horizontal line at this point. This is so much easier to compare, even visually. Okay, however, we will also need columns bin. Columns bin is kind of the same thing we did here, but we have to construct a binary out of the nth digit of each line. So let's do the same thing. Let's say columns bin. So here, we take the lines, and then we're going to do something across all of them. How do we do this? Is there some sort... Do we have a generalized unzip function in Elixir? Because that's really what I want. I want like a massive unzip or a transpose. First off, unzip. It only works on 2 tuples. That's unfortunate. Do we have a transpose? We don't have a transpose. It's kind of interesting that a zip works on tuples of any size, but unzip only works on 2 tuples. Is the documentation just wrong here? Okay, so this still runs. Let's do a new code block here. So, does unzip work? We know the answer to this, but might as well try it out. So, enum unzip. This works. It took the first element from each list and the second element from each list. And now what if we do a 3 tuple instead. It did not work. The following arguments were given. Okay. We could do repeated unzips ultimately, but is there such a thing as enum flatten? Not enum, tuple flatten. There is of course no tuple flatten. So how do we do this? I'm going to just, before we actually try to write it in our big code here, let's mess around with it here. Let's figure out how to do this. So these are our lines essentially, and we need to construct the list. Our target list is what? Really what we want is a list, and then the first element is going to be A and B. And then we want another list that is going to be 1 and 2. And then the third list that is going to be A and B. Target. This is what we want to construct. And here we don't actually have tuples, we have lists. Or rather we have strings, but we can easily convert the strings into char lists. So this is clearly going to be a reduce of some sort. And I bet we start with a list. Well, we're trying to construct a list, so the accumulator should be a list as well. Then here, we get a what? Here we get the first row and then the accumulator. And now we have to do something across each row, each element in the row. So we take the row and we part it into another reduce. The accumulator has to be the argument, so now we have lm, let's call it L, and the accumulator. What do we do? Well, we know that the accumulator has the same length as this. So really, this is sort of a zip, isn't it? We have two lists of the same length, and then we have to do something with the corresponding elements. So, do we have zip width? We have zip width. The zips the corresponding elements from a finite collection of enumerables into a list. Oh, so maybe we just want a zip width in general. What happens if we just call zip width? So, never mind this. What happens if we do enum zip width? What does zip width? It takes a list of enumerables. Okay, and then XX and... perfect. So we just want a zip width with the identity function. Lovely. And we can code call this and just call it and 1. This is the really short shorthand for defining Elixir inline functions. Okay, so here back to our column spin. We have our columns, and first off, we have our lines. And first off, we map over them and turn them all into char lists. Next up, we just call enum zip width, and this should do something. And here we have an argument. The argument is just a really short, our shorthand. Okay, so this generated something. Did it generate the right thing? So the first column should be hash dot hash dot and hash. Okay, and the last column should be dot hash dot. Okay, this seems to work. And now we just have to do the same thing as above and convert this to a number. Convert this to a binary number. What did I do wrong? Oh, we need to put this into an enum map. This explains why we were missing one level of indentation. And now we also have to turn this back into a string, because we had converted it into a char list above here. We converted it into a char list here, so we now have to convert it back into a string here. Okay, and now we have column spin. The first example reflected across some column, I remember. Here probably. So we have 37, 66, 103, and 24 on one side, and then 37, 66, 103, 24 on the other side. Okay, so now we have our input completely parsed. Next up, we need to actually find the reflection points. And the end result here is summarizing all of your notes. You add up. So we're going to be computing a sum of something. And for each pattern, if we find that it reflects across a column, then we have to do 100 times the index. And then if it reflects across a row, it's just the thing. And then we sum up all of these things. Okay, so enum.map, we do something for each pattern. And we can just map on columns. Oh, and in fact, the computation we do on column spin and line spin is going to be exactly the same. So we'll be able to abstract that. Column spin, line spin. And we no longer care about the lines at this point. So, and what do we return? We return find reflection of columns bin times 100 plus find reflection of line spin. Add up the number of columns to the left of each vertical line. Also multiply by 100 the number of rows above each horizontal line. So it's close this. So here it's the other way around. The rows have to be multiplied by 100, but the columns don't. And now we just have to write find reflection. We will put this function in a module because Elixir doesn't like top-level functions. And while we're at it, we're also going to move the parsing into its own module. Def module part 1. So first off, read input. This takes a Kino input as an argument. And it's this whole thing. Putting this in the module has other advantages as well. It also means the code gets compiled rather than evaluated, which is a few orders of magnitude faster. And we are doing some actual processing here. Okay, Kino input read, instead of example, we now have input, because that's our argument. And then here we also have find reflection. Find reflection. This is going to be nums. And we're just going to return 42, which is a nice number. To return that, let's just return 0. Now here, we move this into its own function, so we can do part 1, read input, example. Then we can delete this whole thing. And now if we execute, we get indeed 0 and 0, because that's... Oh, we can delete this. So we got 0 and 0 because that's what our find reflection returns. Now we need to actually find the reflections. So we're going to do this in a brute force sort of way, because we know that there are only like the maximum length of this list is 72. So yeah, there's no reason to... The maximum length of nums is 17. So there's no reason to optimize at this point. We might have to optimize for part 2, but not for part 1. Let's also add a guard here. When is list nums. This will save us in case we pass the wrong type of argument to the function. Now, find reflection. First off, we start with nums. I realize that here, let's just return this as a tuple for now, and we're going to do the multiplication later. Okay, nums. I'm returning it as a tuple now because then we can execute the code and see what we're doing. So for example, first thing we're going to do here is we're going to call with index to annotate each element in each list with its index. Now we're going to check we're going to check for each index if it reflects. Is this called find? Because we only really need to find the first reflection point. What does enum find actually do? Returns the first element for which fun returns a truthy value. Okay, the first element, which will include our index, so that's what we want. And here, we're going to get... interestingly, we don't... This is a bit asymmetric, because technically we should be checking for the reflections between elements, not at each element position. But we're going to say that we're checking for a reflection that starts with this element. Right. So n, and let's call it index. And now in order to check for a reflection, we have to go both forward and back in this list. So how do we do this? Let's just do this the simple way. So forward is going to be nums, our list of numbers, and then we drop idx elements. Right, so for the first one we drop 0 elements, and then for the second one we drop 1 element, which is this one. So for each element, this is going to be basically the rest of the list. So for element 2, it will be this list. Then we're also going to somehow get backward. And to do that, we're going to nums enum.reverse. Okay, so now we flip it, and then we're going... No, first we do enum.take idx minus 1. So now for this element, this is the forward list, and this is the backward list. But the backward list we have to flip. So now we pass this into enum reverse. And there's probably a split function that does the drop and the take simultaneously. And yeah, we should just use that if it exists. Is there a enum split? Enum split splits the enumerable into two enumerables, leaving count elements in the first one. Okay, so yeah. I'd rather use a single function here because that makes sure we don't have any off by 1 errors in this computation here. Like, we probably didn't, we almost certainly didn't, but why risk it? Then backward is backward reversed. And that's how this actually works. Let's return forward and backward. And we in fact do not care about the character itself. And this is an enum find. Let's turn it into an enum map. Let's see what this returns. Okay, so first element and then all of the... Actually, let's look at the second. What is this? This is columns. So there should be a reflection somewhere in here. And where is it? This is wrong. It's not correct. Oh no, forward always starts with 489. Why does forward always start with 89? Because I'm doing this. Backward is actually the first one. Okay, so somewhere in here there's a reflection. And here it is. The first list, 37, 66, 103, 24, 37, 66, 103, 24. So here's our first reflection. And then there shouldn't be any reflections there, but there will be a reflection in the columns of the second pattern. And here it is. 503, 103 to 165, 503, 103 to 65. Okay, so now we need a function that takes two of these lists, and checks if one of them is a prefix of the other. And we don't know which is a prefix of which. So the way we're going to do this is we're going to compute the length of both of the two lists. We're going to compute the minimum length of the two lists. Length of backward and length of forward. And this makes no sense. The length is IDX. The minimum length between them is going to be IDX. And also, we should not be looking at the first one. Right? Yeah, we should not have an empty list ever. Okay. So this IDX is actually going to be called len. And then we're going to take enum.take len. And forward is forward passed through enum.take len. And now we should be able to see our actual reflection here as two identical lists. These are not the same length. Because len is not necessarily the minimum length. It is the minimum length in half the cases, but not in the others. Okay, so length is going to be min of length backward and length forward. Okay, now we only have lists of the same length to compare. And here is our reflection point. And here is our reflection point. Now we just have to return if forward equals backward. And there's certainly a way to write this more efficiently, but this is very easy to understand. And we've already established that we don't need to optimize this because the numbers are so small. Okay, and then here we actually have to return the second element. Because we only need the IDX. What did I do incorrectly here? Oh, because it might be nil. Of course, it might be nil. Oh. Case do. If it's a nil, then it's a nil. Otherwise, if it's a thing, then we'll return the second element in the tuple. And in fact, if it's a nil, we return 0, so that it doesn't contribute to our addition. So we have 5, 0 and 0, 4. Is this correct? So in the first pattern, This is at line 5. Between columns 5 and 6, yes. And in the second pattern, well, 4. It has to be 4, right? Yeah. And the first one, and we have to return 405. So we multiply the second one by 100. And then we do the addition here. Yep, and now we do an enum sum. Now this should work. Is this the right answer? 29213. 29213. That's the right answer. You are 1 gold star closer to restoring snow operations. Nice. So this was very simple. We just followed the algorithm. And we could basically brute force it because the numbers were small enough. But now let's see what part 2 has in store for us. This is where it usually gets harder. Part 2. You resume walking through the Valley of Mirrors and smack! Run directly into one. Hopefully nobody was watching. Aha, joke's on you, we were watching. Because that must have been pretty embarrassing. It was. Upon closer inspection, you discover that every mirror has exactly one smudge, exactly one dot or hash that should have been the opposite type. In each pattern, you'll need to locate and fix the smudge that causes a different reflection line to be valid. The old reflection line won't necessarily continue to be valid. The old reflection line won't necessarily continue being valid after the smudge is fixed. Here's the example again. The first pattern's smudge is in the top left corner. This one. If the top left hash were instead a dot, it would have a different horizontal line of reflection. Okay. But why is this reflection better than our previous reflection? Because there has to be a smudge. Every mirror has exactly one smudge, so we can't have no smudges. With the smudge in the top left corner repaired, a new horizontal line of reflection between rows 3 and 4 now exists. Row 7 has no corresponding reflected row and can be ignored, but every other row matches exactly. Row 1 matches row 6, and row 2 matches row 5, and 3 matches row 4. In the second pattern, the smudge can be fixed by changing the fifth symbol on row 2 from dot to hash. Now the pattern has a different horizontal line of reflection between rows 1 and 2. To summarize your notes you summarize your notes as before, but instead use the new different reflection lines. In this example, the first pattern's new horizontal line has 3 rows above it, and the second pattern's new horizontal line has 1 row above it, summarizing to the value 400. In each pattern, fix the smudge and find the different line of reflection. What number do you get after summarizing the new reflection line in each pattern in your notes? Why is this summarization value 400 here? Shouldn't it be 301? Summarize your notes as before, but instead use the new reflection lines. The first pattern's new horizontal line has 3 rows above it. It does indeed have 3 rows above it. Am I misremembering what this means? No. This is 4 rows and 5, so we definitely take the number of things before. Yeah, this value of 400 makes no sense. We summarize, where do we multiply by 100? 100 multiplied by the number of rows. 100 multiplied by the number of rows should be 300. And this should be 301, not 400. It's also not off by one error, because if this actually had to be one higher than we thought, this would be a 4, but then this would be a 2, so it would be 402. So I think this number is just wrong, and it should be 301. No, because they're both rows this time. That's the specialness. So this is not 300 plus 1. This is 300 plus 100, which is 400. Okay, so all is well in the world. The example is not wrong. I mean, you can definitely brute force this, because there weren't that many patterns, and there are only 70. The biggest pattern is 17 by 17. So if we just do a little math here, 17, so our current algorithm is essentially quadratic, so it's 17 times 17. Then we can, what happens if we add another 17 times 17 possibilities? We get this many integer comparisons per pattern, and there are not that many patterns. I don't know how many patterns there are here, but it's a small number. I normally say that we can execute about 100 million operations per second. So what's 100 million divided by this? How many patterns can we have before we actually go over 1 second? So as long as we have less than 1,000 patterns, we should be able to execute this in less than 1 second. So yeah, let's brute force this. And then if brute forcing doesn't work, we will do something cleverer. So let us now start part 2. We create a new block. Let's call it section 2. In it, we have an Elixir block. Our input reading is similar to before, except we also need to generate some more possibilities. So let's just copy this. Let's just copy our read input and then do stuff with it. Might as well start by putting it into a module, because we're going to do that later anyway. Okay, this is the same read input as in part 1. Let's see that it works. Part 2, read input, example. It does work. Now we have to generate all of the possible smudges. That is, we have to flip every bit. How do we flip a bit? Is XOR the way you flip a bit? Elixir XOR. How do you do XOR? The XOR. Does this have a nice inline operator? It does not. So BXOR. Bitwise BXOR. Let's say 7, which is 111. Let's do 1. Okay, this flipped the last bit. 2. This flipped the second bit, and 3. No, and 4. This should flip the third bit. What happens if we have... What was this again? This was 5. Let's say we start with 5, which is 101. What happens if we flip 1 bit? That works. 2. Okay, so BXOR is how we flip bits. So we have to take our columns, and then the same for our lines, take each number, and for each number, flip each bit. They miss a factor. But when we flip a bit, we have to make sure we flip the corresponding bit in the other one. So if we flip a bit in the first column here, then we will have to flip a bit in every one of these as well. Now instead of flipping bits, let's flip characters. That's also going to be a bit easier to reason about. So we're going to take this. We need a function that takes an array, a list of lines like this, and then returns a list of lists, which is the list of lines, but with one character flipped, with each of the characters flipped. Okay, so this is going to be called generate smudges, and it will take a lines, and this has to be a list. And for those of you wondering, there are plans to add a better type system to Elixir, or a type system that catches more errors. But it's currently in the research. Phase, so it's unclear if the research is going to be successful or not. I think Joseph Alim's keynote at ElixirConf this year was about the type system. Anyway, and we need a better type system because this checks that the top level. This will catch at runtime if the top level isn't a list, but it didn't actually check that all of the elements in lines are strings, which is another thing we'd like to check. Okay, now let's actually generate this thing. How do we do this? Do we have some way of replacing a character in the middle of a string? Let's string to chars. Oh, this is the toString thing. Okay, string. What functions do we have? We have a replace function of some sort. We have a replace pattern matching thing, but I don't want to replace pattern. I want to replace at location. There doesn't seem to be one here, presumably because Elixir strings are Unicode, and iterating through the Unicode graphemes is inefficient. But our strings also happen to be binaries, not binary numbers as in ones and zeros, but Elixir binaries. And surely there's some way to flip a byte in a binary. Elixir replace a byte in a binary. I'm sure we can do it with pattern matching, but maybe there's a function. Constructing a new binary like that would result in Erlang having to copy the whole binary. One option is to use map. Yes, but I do actually want array. It must be... What's array? Array gives us an array, and then we can do array set on it. This is the sort of thing that would be much easier in a less pure language than Elixir. Curiosity, can I do pattern matching on binaries? How does pattern matching on binaries work? Let's say we have the string hash dot hash hash dot dot hash hash. This is called str. Now I can do a binary pattern matching and say A, which is binary size 2, and B, which is the rest of it. Now what are A and B? So this is how we pull out 2 bytes and the rest of the bytes. But now, can 2 be a number? Can 2 be a variable? What happens if I do binary size of n? This still works. Now what happens if I here do binary size instead of, so 6 would be the thing that gives us everything, but I want 5. Oh, in fact, what if I do this? Now this should give us the first n bytes, then drop a byte, and then all of the other bytes. So it's hash dot, then it drops a byte, and then it gives us the rest of the bytes. Okay, and now x. And now we can have x here as well. Right? And x we can flip. So x is, if x is dot, then we do hash, otherwise we do dot. And here we can reconstitute this into a full binary. Does this work? No, this is an integer. Expected an integer, but got like this. Okay, so now we have hash dot. Then we flipped the thing on position 2, and then we got the rest of it unchanged. Okay, so this is how we flip characters in our strings. So now we have to go through every line and every column and do this sort of flipping. All right, let's get to it. The other annoying thing is now we have a way of flipping things inside of a string. Actually, no, let's flip all the character. Let's generate all the possibilities here. Like if this, I'm still finding this hard to write, so that just means we have to do it more piecemeal. We'd have to do more pieces outside. So let's do, we're going to have to flip all of the bytes. So let's do 0 to length of str minus 1. Then we do an new map here because we have to generate something for each element of this range. And this is going to be idx. And now this should give us all of the possible flips for this one string. First argument, not list. Where? Oh, this is a string length, not just a regular length. Okay, so flipped the first one, flipped the second one, flipped the third one, flipped the fourth one, and so on. This worked. So this is how we generate all the possibilities for a single string. How do we do this for a list? Rather, how do we replace each element? How do we generate a new list of strings where one element is different? Presumably we do string split. Let's try it out. So here, we again have to do 0 to, this time it's a regular length of lines, minus 1 because Elixir ranges are inclusive on both ends. Now I have to do a new map, and then here we're going to call this line number. And what do we do with our line number? We have to get all of the strings before and after this. So we're going to do before. Yes, before and after. before and let's call it after underscore. Yeah, after is a keyword in Elixir, and I don't know what the parser will do if we try to use it as a variable name. So before and after, enum.split lines at line num. Now we actually break after into two things. We're going to break after into line and constant to the rest of after. And in fact, here we don't go to lines. Do we go to lines or not? What happens if I run this? Let's return before, line, and after. Here, let's just call part2 generate. So here, we do lm.add0. Let's just look at the first example. Enum. This is just the first example. And then let's just call then generate smudges. And we have to call this on lines, so it's .1. It's the first argument, lines. And it's not to just generate smudges, it's part2 generate smudges. Okay, so this generated an empty list at the beginning, then the first line, and then all the other lines. And then it went all the way to everything in the first list, then the last line, and then an empty list at the end. Okay, this is correct. And now we need to do all of the we need to generate all of the things here. We need this. And we're going to use this to modify line. So it's not str, it's line. And now this generates all of our new possible lines. This is actually a bit hard to read if we write it like this, so let's not use the pipe syntax for once. Okay. Now we have the enum, we generate all of the new lines. And now we have to reconstitute our our whole list. Should look like this. Where's str? This is line. Okay, this looked like it generated kind of what we want, but it generated the correct thing. So all of these lines should be identical, except, and we're going to remove the extra level of mapping, we're going to remove the extra level of nesting in the list with a flat map later. But for now, let's just leave it like this. So every one of these lines should be one of our new lines with smudges in them. So all of them should be completely identical except for one character which is flipped. And the character that is flipped is this one here. Right, so this is the original. Then, oh, in fact, there should be two characters flipped every time because it's the unflip. We're seeing the first version with a flip and then the second version with a flip. So we have to unflip one character and then flip another. So this is the change here, then this is the change here, then this is the change here, then this is the change here. I am noticing a pattern. And this is the change here. All right, this seems to be working. So next up, we flat map this. So now it's just a list of lists. So now we have all of our generate smudges. And what do we do with our generate smudges? What do we do with these lines? Well, first off, what we do is we create the bins. We now need to create the bins, the call bins, and the lines bins. So here, we don't actually want to do that at the very start. We want to do def generate bins. And this takes a map that has lines in it. And it will return a map that has, it will return the data map, but also with lines bin in it, and also with columns bin. And here we go. This is how we generate. Yes, this is how we generate the lines bin and the columns bin. And this should still run, because we're not using undefined variable lines bin. Where is this? Part 2, line 9. Here. Right. We do not have columns bin and lines bin anymore when just reading the input. Okay, now we pipe this into enum.map. Note that we're still doing this just on one example. We'll do it on all the examples, on all the lines. We'll do it on all of the patterns later. For now, we just take this, and then we just call part 2, generate bins. Because this is not smudges. So here, we need to regenerate our map. Up. What's going on here? The following arguments were given to part 2 generate bins. Alright. New thing. When we call generate smudges, we don't actually expect the lines, we expect the whole data thing. And we will generate a new data thing. So here, when we actually generate the lines, we will in fact generate a new data map with the lines replaced. Okay, columns bin not found. This is on line 33. Line 33, columns bin. Because this is the replacement. This is the syntax for replacing a value in a map. We in fact want to do something different. We want put lines bin, then put again, columns bin, columns bin. This here is an underscore. Undefined, what do you mean undefined function put 3? What's the syntax for put? Don't need this, here, put. Map.put. Wait, no, what I want is put in. This definitely exists, right? Put in, puts a value, put in, data keys value. Okay, so reloading really quickly to get Livebook in a good state after a weird interaction with Wayland and the clipboard. Okay, where are we? Where's my put? Part 2. Let's actually collapse part 1. Okay, part 2 here. This is put in. And put in. This is a list. Okay, and now we have all of our possibilities. And now I have to call find reflections on this, which should just work. Dot map. In fact, we just need to find the first reflection, don't we? They never actually say this, but I assume we want to find the first reflection. So our reflection function, our find reflection takes... Basically, we want this, except it should return... Yeah, so we're going to take this. Find reflection. And it's going to take something out of data, but I don't know what yet. And so it's going to take columns bin and lines bin out of data. In fact, we probably don't need data at all. Here. And this just calls part1 find reflection. However, there is now a chance that there will not be any reflection. So what we actually want to return is this or this. And this will return a nil in case there's no reflection on either one. But that's not good enough because for the lines we actually want to multiply by 100. Okay, so find reflection columns. If we did find a column reflection, then we're done. Otherwise, we call... Let's just write this explicitly. Case do. So if we return an n when is integer of n, then we just return n. If we got a nil, then we have to do part2 find reflection. And we're just going to do another case here. We can do this with short-circuited Boolean logic, but it will just look uglier, a lot uglier. So when it's nil, then we return nil. When it's n, we return n times 100. Here we can actually move this afterward, then we don't need the guard anymore. Alright, so now we call part2 find reflection. Part2 find reflection is undefined. Reflection with an E. Okay, so it found a bunch of reflections. That's interesting. In the first example, it found a bunch of reflections. In particular, it found it in the very first one. So there's a reflection in the first element here. Let's see. And it said 5. 5 means it's on the columns. And there is indeed a reflection. Yeah, there is indeed a reflection around 5. But they said, is this the same reflection as at the start? Shouldn't be, because this is not the same line as the original example. Yes, we changed this. This has been changed. This has been changed to a dot. So these numbers are definitely different from part 1, and yet there is still a reflection around the 5th column. Which makes sense because the 5th column never actually checked the first line, so... Right, so if this is changed, then 5 is still a valid reflection. Okay, so the first pattern smudge is in the top left corner. If the top left hash were instead a dot, it would have a different horizontal line of reflection. But why is the horizontal line of reflection better? Because it's smaller? Because it's a 3 instead of a 5? They don't actually say. Does the word least appear? No. Small. No. So they don't actually say which reflection wins in case there are multiple reflections. So let's assume it's the smallest one. Yeah, let's assume it's the smallest one. Here, part 1, find reflection. This returns a 0, not a nil. So here we want 0 instead of nil. So now if we call find reflection here, we get a bunch of things. Let's do a new map and print all of these. It only ever finds the 5s. I don't see any 3s. Which is incorrect. It should definitely find this reflection here. Okay, but it's telling us that the smudge is in the top left corner. So can we debug this? Oh, this is frustrating. So actually what's going on here is that find reflection is only looking for the first reflection, isn't it? Yes. But as it happens, no, we're trying both. We're trying both the reflections on the columns and the reflections on the lines. So it should have found... No, here. We're trying the reflection on the columns and not on the lines. So we actually need to do both of these. And we need to find the minimum that is greater than 0. Ugh. Okay, so let's call this C. I'm not sure what the logic here needs to be exactly, so I'm just going to write it out bit by bit. L is this thing. Okay, so if C is 0, then we just cond 2. If C is 0, then we just return L. If L is 0, then we just return C. If C. If neither is, if true, if both of them are non-zero, then we return the minimum of the two. Now this should return a 3 on the first one. Yes. This returns a 3. And here maybe we don't have to do a map, maybe we can just do a find, where we take the data, call find reflection on the data, and case do. If this returns a 0, then we return a nil. Otherwise, we return the n. This returns a false if it's a 0. This returns a true otherwise. And we don't want find, we want find value, right? We want enum.find value. Similar to find, but returns the value of the function invocation instead of the element itself. Okay, so this has to return nil, presumably. Nil and n. What happened here? I was not expecting it to return a whole find value. Protocol enumerable is not implemented for 3 of type integer. Right, we can no longer do enum map on it. This returns a 3. But here, if it's a line, we also have to do times 100. Right? Oh, and here, in fact, we have to do more complicated things. If L is less than or equal than C, then we do L times 100. If C is less or equal to L, then we just do C. And this returns 300. So now here, let's get rid of this enum at, and then basically everything afterward has to be done in an enum map. So enum map pattern. Is pattern what we were calling these? Guess we weren't really calling them anything. Pattern. All right, and now this should return 300 and 400. Summarize your notes as before. Wait, why did the second one return 400? Or second one should have returned 100. Okay, so let's debug. Here, we do enum drop 1. We now only have the 400, so we can print out more things. Here, we can do, there's a find. This is probably the problem. We probably don't want find, we probably want min. We want min. Let's just do map for now. Okay, yeah, so we want min, in fact. Min when it isn't 0. So here we do first enum.reject. No, first we do enum.map, and then we just call part2.find reflection of arity 1. Then we do enum.reject, where the argument is 0. And then we do enum.min. This returns D, which is presumably 100. Why did it return it as a character? Oh, this returns a list of 100. Okay, and now this should return a list of 5 and 100. Right, because the columns aren't multiplied by 100. This is annoying to write. Alright, so in find reflection here, we clearly can't return L times 100. So we return lines L. And this is columns C. Is this good? Well, it's the same whether we put it as, whether we put the annotation as the first element of the tuple or the second one. Okay, so now we generated the bins. Then we find the reflection, and then we reject anything where the second argument is 0. Then we need something that sounds like enum min by. And this is exactly it. Returns the minimal element in the enumerable calculated by the given function. So, enum min by. Function is this and n. Then it just returns n. Now, at the very end, we actually look at what the first thing is. Let's call it tag and n. A sub tag do, if it's lines, then we return n times 100. If it's columns, we just return n. Now we get 300 and 100. And if we sum this up, we get our answer. Alright. Now let's do this for the full input. Okay, that took longer than expected, 2.4 seconds, but presumably I'm just... Okay, so this probably needs to be put in the module to speed it up. Okay, let's do def calculate. This takes a Kino input. We're just going to move this whole thing into a function. And here, instead of reading full, we read input. So now we have part 2 dot calculate a full. This should be faster than 2.4 seconds. Really? 2.1 seconds. Well, it was definitely faster. 2.2 seconds. It was a less impressive speed up than I had hoped. Anyway, let's see if this is the right answer. 17,549. 17,549. That's not the right answer. Your answer is too low. So it's presumably not the minimum. Okay. What is the actual reflection we're supposed to return? The first pattern smudge is in the top left corner. If the top left hash were a dot instead, it would have a different horizontal line of reflection. Why does it have a horizontal line of reflection? Does horizontal trump vertical by any chance? The mirrors are extremely shiny. You noted that the patterns of ash, dot, and hash that you see as you walk. Perhaps by carefully analyzing these patterns, you can figure out where the mirrors are. To find the reflection in each pattern, you need to find the perfect reflection against either a horizontal line between the rows or a vertical line. So let's assume that horizontal trumps vertical. Let's assume that this means that horizontal trumps vertical. Alright, so how are we doing this? Here. We just have to change this find reflection function. We're going to just copy it and leave the last one, leave the original one unchanged. Okay, find reflection. So if we find a reflection across lines, so if L is different from 0, then this is the reflection. Otherwise, if columns is different from 0, then this is the reflection. And otherwise, it's neither. So we're just going to say lines 0, because it doesn't matter. And now this is going to, now we generate the we find the reflections here, then we filter out all of the zeros, then we find the minimum one. This minimum one isn't correct, is it? Right, because we now have to do find again. So here, really, when we do find reflection, we just want to do find. So here, it's L times 100, and here, it's C. Then that's it, right? Where are we? No cond evaluated to a truthy value. So if it's neither of these, then we return a nil. And then this is not underscore, this is true. Add argument in arithmetic. Right, here we want to do find value. And this is indeed a much smaller number than we tried before. But let's try it on example first. Does it give the right answer for example? It does not. Why not? Because there are multiple possible reflections. So we still need to do the minimum here. Right? Yeah. So we do find reflection. It's just that we need to prefer the lines over the columns. Here actually here we're just going to reject all of the nils. And then we need to find the minimum. But the minimum has to prefer lines. So actually we have to sort. Oh, that's not even true, right? I just have to add a 1 here or something. Let's call it AAA. Actually, instead of this, let's just say 0. Here we say 1. And now this should sort properly if we just do min. And then here, if the tag is 0, then we do times 100, and if the tag is 1, then we do just n. Let's try this out on the example. Where is this? Line 67. This card will always return, yes, this is true. No clause matching columns bin at line 81. Okay, we're doing the rejection, then we're doing then. If I do an IO inspect here, what do I get? I get columns bin. Why? Because I still have a find here. This should be a map. Right. Okay, this now works. Let's try it on full. This is a different number from before. So 38567. 38560. 38560. That's not the right answer. This answer is too high. Okay. Okay. So are we prioritizing? We are definitely prioritizing lines correctly, right? We call find reflection here, then we reject, then we do a min. And the min will do what I think it will, right? And delete this. Let's see how comparison actually works in Erlang, maybe. So, is 0, 100 less than 0, 200? It is. How about less than 0, 50? No. How about if we change a 1? Yep. And then how about if we do 100? Yeah. How about if we do 200? Okay. So comparison works as expected. This tag thing is correct. So here we find the minimum. Then we find the tag of the minimum, and then we multiply by 100. And this said the number is too high. So they're claiming there is, in fact, a smaller okay. You need to find the perfect reflection across either a horizontal line between two rows or across a vertical line between two columns. So we are prioritizing rows and we are deprioritizing columns. In the first pattern, the reflection is across a vertical line between the two columns because there's no horizontal reflection. In this pattern, fine. And then here, the first pattern smudge is in the top left corner. If the top left were instead the dot, it would have a different horizontal line of reflection. In each pattern, you will need to locate and fix the smudge that causes a different reflection line to be valid. But, so are we looking for the smudge that causes the minimum reflection? Well, our number was too big, so presumably we need to find an even smaller reflection. Okay. With the smudge in the top left corner repaired, the new horizontal line of reflection is between rows 3 and 4. So the first pattern's new horizontal line has 3 rows above it, and the second pattern's new horizontal line has 1 row above it. Which is, yeah, this looks right. Okay, let's try this on the example again. And then here, let's just not do our minimum anymore. Let's see what we get. So we get 0, 3, 300, yes. And then we could also have reflected across the fifth column, and then many more fifth columns, and then yeah, and then across the third line again. And for the second example, it's a 0, 4. 0, 4, 0, 4, 0, 4, because we can always reflect across the fourth line. But there's also one example when we can reflect against the first line. Really, so in the second example, we reflect across the fourth line because, of course, these 3 are reflections. So replacing really any character on the first line doesn't actually break our reflection here. This is how it worked in part 1 as well. The only interesting thing is that if we change the fifth character, then we can now reflect across the first line. If we change the fifth character, we can reflect across the first line. This indeed results in, right? This results in 0, 3, and 0, 1, as expected. Three, 8, 5, 6, 0. 3, 8, 5, 6, 0. If I try submitting this, your answer is too high. But we're literally finding the minimum here. It shouldn't be possible for it to be too high. Unless find reflection here doesn't actually find the smallest reflection. And what does find reflection actually do? It does have a find in here. So sort of by process of elimination, this must be the place where the bug is. But it can't be because we're going from low to high. Although we can make this more obvious. So we start from 0. We start from 1 because we're dropping 1, and then we go up to length of nums minus 1. And we no longer have the first element in the tuple here. So this should not change the result. 2, 9, 2, 1, 3. Yes. Okay, now we're obviously going through these in order. And we find the first element, but that's correct, because the first element will be the smallest one. Okay. And then here, we generate all of the smudges, so this can't be wrong. Generating the bins, again, can't really be wrong. So this means that the bug must be in find reflection. Find reflection. It tries to find all of the reflections on the columns and all of the reflections on the lines. And we know that lines and columns are correct because they were correct in part 1. And in fact, we can refactor this a bit to prove that that is actually the case. So we're just going to replace our read input functions from part 1 with the ones from part 2. We have read input and generate bins. Then we can delete this. Here, we do read input, and then the next step is input map. Part 1, generate bins of arity 1. If I run this, the result should be unchanged. Now here, I can delete this. We can delete this. Yes, we are using the plural we. We are using the plural we. So now, this should still run. And it should give the same result. Right, it's not part 2 generate input, it's part 1 generate inputs. This is part 1 read input. Yes. Okay. So now we are sure that read input is correct. Generate smudges is probably correct, although we'll have to check it again. Generate bins is definitely correct. Find reflections. This is likely where the bug is. So we try to find the reflections in the columns and in the lines. Then the lines take priority. because we always look for reflections in the lines first. But if there isn't a reflection in a line, then we'd look for a reflection in a column. Okay, so we call find reflections, then we filter out all of these nils because they're unhelpful and they shouldn't matter. Then we find the minimum. And the minimum will prioritize these tuples. And then we just convert this into the right format. If it's a 0, then it's times 100, otherwise it's 1, and then we sum up. And this doesn't work. So instead of enum.min, let's do enum.sort. I'm curious what this will result for the example. Here, we don't need we don't need that code block anymore. Okay, so here, input 003. This looks like it's sorted correctly. Okay, now what happens if we run this on full? Prints out a bunch of stuff, which is unsurprising. It kind of cuts off, which is annoying. Okay, but does the sorting look right? The sorting does look right. It's always 0 first and then 1s. Let's also do a dedupe here. This will improve our output. Okay, yeah, this is much better. So if I do this on example, we should just see the possibilities, right? Yeah, so the possible reflections in the example were across the third column as always, and then across the third line, and then across the fifth column. And then for the second one, it was across the first line, and then across the fourth column. So now, what does this look like on full? It was either across the first line or it was either across the 7th line or the 14th line. 5th line, 10th column. This one had just columns. A lot of them are just lines. And a lot of them have only one possibility. Well, some of them have only one possibility. Interestingly enough, so we're not doing any minimum here, we're just doing deduping. So a lot of them have either one possible reflection or two reflections. None of them seem to have three possibilities. But if we take the minimum of this, unsurprisingly, we get just this. And then this result is too high, right? So if I now... let's just check. This should still yield the same result as before. It does. Your answer is too high. We're generating all of the bins, and then we're generating all of the smudges, then generating the bins, then finding the reflections, then rejecting, sorting, deduping. So there is no way we are missing, there are no finds in here, so there's no way we're missing something. So this means generate smudges must be incorrect. Okay, well, let's test it out. We are going to do part 1 read input example, part 1 read input example. Part 1 generate smudges. Actually, no. First, enum at 0. Okay, and now we generate smudges on this. Now, how many did we get? We got 63. This seems like a suspicious number. No, this seems like 7 times 9. Was 7 times 9 correct? Lines. Let's return the length of the lines and the length of the first line. Seven times 9, which was 63. So this indeed generated 63 smudges. Now, what if I sort? So this just generates a map with lines. Okay, what if we sort and dedupe? It should still be 63 because every one of these is different. Okay. Are we generating the right smudges? We must be. Let's check. How do we check? We are going to enum over them. Enum with index first. Enum.map. We take our first element is going to be this thing with the lines. And then there's the index. And we do IO put s idx. This probably needs to be a string. And then on each of the lines, we do another enum map, or rather a for. Add arity. This is the tuple, of course. Okay, let's add another IO put s here so that we have an empty line between smudges. Right. Now the first smudge is just we replace the first character. We should do this and print out the actual first example as well. Where's IDX? Here. This is not called IDX, this is called original. Let's just return a single OK at the very end of this. Okay. Now we can see the original and the first one. And it's identical except that we flipped this one hash here. Yes. Now let's see if we get to the very end. I never actually checked this. We didn't check this earlier. So the very end one should be the 9th, the 8th here. And it worked. All right, and then the next one should flip this character here. And it did. Okay, so this seems to be working. And the last one flips the last character. Yes, the last character. So generate smudges is correct. Your answer is too high. Your answer is too high. But there has to always be one smudge, right? Return to day 13. Every mirror has exactly one smudge. So we cannot have a mirror without a smudge. We need to locate and fix the smudge that causes the different reflection line to be valid. This 400 value is smaller than the 405 here. But I think that's incidental because we have to replace at least one character. So summarize your notes as before, but instead use the new reflection lines. This pattern. How do we summarize? To summarize your pattern notes, add up the number of columns to the left of each vertical line of reflection. To do that, also add 100 multiplied by the number of rows above each horizontal line of reflection. Multiply 100. In the above example, okay, this is exactly what we're doing. Okay, I am generally stumped. I think this should be correct. We can't be overflowing or anything of the sort because we're using Erlang. We're using Elixir, which is Erlang under the hood, which is big num arithmetic. And this is not the right answer because we've tried it several times. Yes. All right. What does the subreddit say? This does not sound like path. Some days are just like that. Me adding a for loop. There are a lot of... What's going on? This is all from yesterday. Sure what they're asking me in the first part. Part 2, more sample tasks. When you check the grid for symmetry, make sure you are searching for the new alternative solution. Grid with one place replaced can have both old symmetry and new one. Yep, we're doing this. Finding more than one reflection line. We're doing this already. We are doing this already as well. This was not helpful. Day 13, part 1. I had never actually looked at the subreddit before, but it's not particularly helpful. Came across a pattern that my code could not find a reflection line for. We're definitely finding a pattern for all the things, right? Reload this. We are definitely finding a pattern because our number is too high. But the subreddit is not helpful at all. Every smudge has an equal and opposite smudge. What? If there is a single mismatch between a dot and a hash, then changing either of these creates the match and it will have the same line of reflection. What makes one of them correct and the other one incorrect? Can you fix every smudge in 2 different ways? So here, we can fix this reflection by either smudging this or smudging this. So but in either case, it doesn't actually matter because the line of reflection is still the same. So we should convert every character. So I find a symmetric vertical split, I stop. Why should I continue searching for symmetric horizontal splits? You'll need to locate and fix the smudge that causes a different reflection line to be valid. The old reflection won't necessarily continue to be valid. Oh, causes a different reflection line to be valid? No, it can't be. In each pattern, you'll need to locate and fix the smudge that causes a different reflection line to be valid. Okay, so we actually need to solve part 1, then find the answers to part 2 that do not actually solve part 1. Ugh. This is... Okay, so subreddit was actually useful. I guess I did actually highlight it, but... Okay, let's solve this. So, we generate all the smudges, then we generate the bins, then we find the reflections. However, when we find the reflections here, it has to be a different reflection than the one we used in part 1. So, we're just going to do part 1. Reflection is part 2 dot find reflection of the original pattern. Of the original pattern that we run through generate bins. Right, and I can now inspect this and it should give something. It should print out something and not error out. Generate bins can only pipe into local calls. Sure. Right, this the syntax here is like this. Okay, it generated a bunch of part 1 reflections. And 38560, this is too big. Reload. Right, now we have the part 1 reflections. So here we're going to reject if x is equal to nil or x is equal to part 1 reflection. And we don't need to print this out anymore. Where is it? Empty error. The hell is an empty error? There's an empty error because you called enum.min and something without any reflections. Okay. We're getting somewhere now. So what happens if we end up with an empty list here? Then let's just IO inspect our pattern. Otherwise, if we get X's, then we do the whole thing from before. All of them are empty. Wait, so we reject if X is nil or if X equals part 1 reflection. What is part 1 reflection again? This looks right. Because here we find all of the reflections. Oh. But we have to discount these things, don't we? Ugh. Okay. FN data. I do not like today's problem at all. Data and part 1 reflection. We're going to pass a list. We're going to pass a list to find reflection, that is the excluded ones. Or the invalid ones. Yes. Okay. So now here we have candidates. It's going to be it's going to be 0 and L, 1 and C. So these are our candidates. And then we are going to do two things with them. First off, we are going to remove the invalids. Then we are going to sort. And then we are going... Oh, damn it. I pressed enter by mistake. And I'm losing my patience, which is not great. Then here we do list.first. And this might break here, but... Right, so there's no guarantee here that we have a reflection, that find reflection will actually find a reflection. Here, first you also have to do enum.reject anything that has a number, a 0 on the second number. N equals to 0. We reject the things that are 0. Then we sort. Then here we have to do two cases. Case do. If we get an empty list, then this just returns a nil. Otherwise, it returns candidates. Then we just pass candidates through the below. Okay, find reflection should be correct now. Then here we do reject, then sort, right. With 0. This printed out something which is a smaller number, but it also printed out a bunch of these, which are probably the patterns where we couldn't find any reflection, which sounds incorrect. If we run this on the example, nothing bad should happen. Yes, but if we run this on full, something does happen. So the part 1 reflections, for a bunch of them were that. Then we found a reflection, one that has a part 1 reflection of 1, 1. This is hard to look at, so let's take this. Yes, let's take this and put it in a function called print pattern. This just takes a map that has lines in it. This should work. And then here, instead of IO_inspect pattern, we do print pattern. In fact, here we're also going to do IO_put_s. Would not find reflection. This makes it clear what we're looking at. So here we go. We could not find a reflection in this. The reflection is obviously this character here. Or at least there is one possible reflection, which is this character. And it is saying that the reflection for part 1 was 1, 1. Was it 1, 1? So it says it's this one. Really, if it's this one, oh, it's 1, 1, so it's around 1 means column and 1 means column. So the reflection in 1 was, yes, it was around this first column here. So we can't have this reflection, which is fine. But this should have found a smudge. There's a possible smudge here. This one. Isn't there? No, there isn't. Because this is not, can't actually reflect. Are all of them guaranteed to have a reflection? You will need to find and locate, you will need to locate and fix the smudge that causes a different reflection line to be valid. But none of our smudges cause, no smudges here cause a different reflection line. Unless the code is wrong somehow. Feels like there's maybe a reflection line along here. Yes, it feels like there should be the correct reflection would be at column 5. And we get that reflection by flipping this. Okay, so let's print out the smudges. Right, yes, this is by far the easiest one. Okay, so let's take this as an input and run our algorithm across it. I don't need this thing anymore, but maybe it will be helpful. Here, let's do test input. If this is kino input text area. We paste it in here. Right. Now we can clear the clipboard and reload. This test here. Let's move this one up in here. Instead of doing kino read input lm at 0, let's just do it on test input. Yes. Test input. And this should output a bunch of smudges. Right, so this is the original, and I said the fix would be, the first fix would be around here. So this is what? 4, 9, 18, 20-ish something. So here we are, and then one more, this one. There's a line of reflection at 25, or there should be. So let's actually compute find reflections and see what it outputs. So part 2, find reflection. Oh, and in fact, here we can just do enum at 25, because we know that that's the one we want. We have to do this earlier. We have to do it here. Enum at, and then this isn't a enum, this is a then. Right, so this is the one that should work. Shouldn't it? Ah, no, there isn't a reflection here. Yes, this doesn't actually reflect. Wait, so is then the reflection at the very end? Looks like it might be. Here we go, this one. Is this the right reflection then? So it would be around this point. Yes, this looks like plausible reflection. 61. Okay, now let's print the reflections for this. How do we print the reflections? Part 2, find reflection of data. Here, this is data. And here, let's just do part2.find reflections of data. No invalid, and I'll inspect. Oh, and we also need the data to have bins generated for it. Data part2.generate part1 generate bins. Yes. It just finds 1, where it should also find, because it only finds the first one, of course. Right. So remember earlier when I looked at part 1 and said, here we go, that this is definitely correct, because although it's a find, it is going through them in order, and therefore this is correct. This has to find the smallest one. Well, the smallest one isn't correct anymore. The smallest one might be filtered out at a later stage. So here, this is now going to be a map. Yes, there's no case where this might return a nil here. This will always return a list. This is no longer called find reflection. It's now called find reflections, plural. And here, we do find reflections and find reflections. And in fact, we have to do enum.min of this. Because in part 1, we actually just care about the smallest one. And now the result should not change. The result is 29213, correct. Arithmetic error. Enum.min. So here, what was it? If. Okay, if it's this, then we return IDX, if I remember correctly. Yep. Else, we return what? We return nil. And we can actually filter out the nils here. So empty error. Right, this might return an empty list. This was so much nicer before. So if this is not going to work because empty is going to fail. I need an empty with a 0 value. Columns min is, we take find reflections. And if this is, it's not a condition, it's a case, do. If this is an empty list, then we return 0. Else, up x's, we return enum min of x's. This is columns min. And then we have to do the exact same thing for this one. Let's just say def min reflection x's empty list. This is going to return 0. Then if it's in reflection, if it's x's, then it will return enum.min of x's. Okay, so this is min reflections. Min part 1 min reflection. And then to this we add part 1 dot min reflection, part 1 find reflections multiplied by 100. Alright, and here we have part 1 find reflections columns bin. Let's return something different. Because again, we have to do the thing where we prefer horizontals over verticals. Why didn't this happen originally? We have to prefer horizontals over verticals. But that should be easy to do here. Right, we just have, oh, in fact, we don't even need min reflect, or we do need min reflection for something. So here we do case. So if we didn't find a reflection across horizontals, then we try verticals. Otherwise, we don't. And now this works again. Okay. Importantly now, we have find reflections. So here, find reflection, find reflections, find reflections. This is no longer C, this is called C's, and this is called L's. And here we're going to construct enum.concat, enum.map C's, and we take a thing, and then we return, if it's a C, then it's a 1, and then the number. And if it's an L, it's a 0, and then the number. Okay, and this outputs something which is smaller than our old one. But let's test this on our test input. We should find a reflection around 61. We should find more reflections around 61. But we did not, so this is still incorrect. Rather, this still says that 1, 1 is the reflection. What happens if we exclude 1, 1? 1, 5. Okay, this works now. So this outputs something. We no longer... Here. We do not need this case anymore. In fact, this case should throw an exception. So we can just delete all of this stuff. We can delete this case. And then we can de-indent this. Okay, we do not need to print out this either. Okay, is this the correct answer? 37453. 37453. 37453. That's the right answer. You're 1 gold star closer to restoring snow operations. Okay. Okay. So, review. Let's look at the problem again. So we just brute forced this. We had to find reflections. We started off by having these patterns, and we had to find the reflection around either a horizontal or a vertical. We did this by converting each of the lines into numbers, since these are basically binary digits. We did the same for columns, and then we just used the quadratic algorithm to try all of the possible reflection lines and reflection columns. And this worked. And then for part 2, we had to do basically the same thing, except we could also replace every character with its opposite. In fact, we had to replace every character with its opposite. So we did that, which was another level of quadratic. Then we did our the algorithm from the first part, which was another level of quadratic to find the reflection columns or lines. So our total algorithm here is n to the 4th power, where n is one of the dimensions of one of these patterns. The trickiness today was that the problem statement is really annoying, and there are lots and lots of corner cases. And we failed to find at least one of the corner cases. This one. Fix the smudge that causes a different reflection line. So if we find the same reflection line as on the first part, that's incorrect. So we failed to see this corner case and had to check Reddit for somebody to point it out. I guess the lesson for the following days is whenever there's something highlighted in white, we need to reread it a few times to make sure we understand why it's highlighted in white. Right. On the upside, this means we are now past the halfway point. We have fully completed day 13. What do the stats look like? So a few more people have solved part 2 from yesterday, but a lot are still struggling. But the numbers are picking up for today, so presumably more people will solve day 13 than 12. Do we need to refactor anything here? Rather, we can delete this bit at the end. That was just the test. Yes. We no longer need the find reflection here. The old find reflection. Yeah. We no longer need that comment. We didn't need this inspect. We don't actually call print pattern anywhere, but we'll just leave it in here in case we ever need to look at this again. Don't need this comment. Can we merge anything extra between part 1 and part 2? Can we refactor? I don't think so. Well, we don't need to sort and dedupe here, do we? The min should just work anyway. It does. We could definitely code golf this a bit and get rid of a few of the intermediary values, but a few of the intermediary variables. But, well, that would make the code less readable and it wouldn't improve anything. We never ended up using our helper section. We just stuffed everything into part 1. Okay, so that's it for today. Thank you for tuning in and see y'all tomorrow.